Take a look outside on a clear night. You'll see the moon, maybe a planet or two, all tracing their familiar paths across the sky. The solar system seems like a perfectly crafted clock, doesn't it? Earth completes its loop around the Sun every 365 days, like clockwork. Jupiter takes its grand 12-year tour, and distant Neptune follows its 165-year cycle. It feels permanent, eternal even. But what if I told you that this beautiful, predictable dance is a temporary illusion? That the very force holding it all together is also the seed of its ultimate destruction. Welcome to the fragile future of our solar system. Beneath the serene surface of planetary orbits, a subtle chaos is brewing. The force of gravity, the cosmic glue that binds our celestial family, is a fickle master. Over immense timescales, millions and billions of years, the gentle, persistent tugs between planets add up. They create tiny wobbles and shifts in their paths, imperceptible to us now, but with colossal consequences for the deep future. This isn't science fiction. It's a story told by the laws of physics and revealed through some of the most powerful supercomputer simulations ever created. The cosmic clockwork isn't perfect. In fact, it's slowly winding down into unpredictability. So, what kind of future are we talking about? The possibilities are mind-boggling. Simulations show a small but real chance that Mercury, the smallest planet, could one day have its orbit so severely disrupted that it crashes into Venus. Or, even more dramatically, it could be flung across the solar system on a collision course with Earth. Imagine that. Meanwhile, Jupiter, the king of planets, acts as both a protector and a potential menace. Its immense gravity has shielded Earth from countless comets, but it could also be the one to destabilize the inner planets. Like a bowling ball crashing into a set of delicate marbles. This isn't just about planets playing bumper cars. The entire architecture of our solar system is subject to change. A planet could be ejected entirely, cast out into the lonely darkness of interstellar space, becoming a rogue world without a star. And this all happens before we even consider the final act, the death of our sun. As our star ages, it will swell into a red giant, engulfing the inner planets Mercury, Venus, and possibly even Earth. Our world could be vaporized, its long history erased in a final, fiery embrace. The once stable system will be completely rewritten. What we perceive as order is just a snapshot in a vast cosmic timeline. The solar system has a history stretching back 4.6 billion years, and its future will extend for billions, perhaps trillions more. We are living in a fleeting moment of relative calm by studying the subtle gravitational interactions and running these incredible simulations. We are peeling back the curtain on our ultimate fate. We are learning that in the universe, nothing is permanent. The serene dance of the planets is beautiful, but it's a temporary performance on a stage of cosmic chaos. How did our solar system become the cosmic neighborhood we know today? To glimpse its chaotic future, we must first travel back to its very beginning. Imagine a time about 4.6 billion years ago. We're not in a solar system, but inside a giant cold cloud of gas and dust floating in the vastness of space. This was our cradle, a giant molecular cloud made mostly of hydrogen and helium. Then, a cataclysmic event, likely a shockwave from a nearby exploding star, a supernova, sent a ripple through this cloud. This ripple was the starting gun. A dense pocket within the cloud started to collapse under its own gravity, spinning faster and faster, just like a figure skater pulling in their arms. As it spun, it flattened into a massive disk, what we call the solar nebula. At the very center of this swirling vortex of material, the pressure and temperature grew so intense that a new star ignited our sun. The sun was born, and it greedily consumed over 99% of all the matter in the cloud. But what about the leftovers? The remaining dust and gas formed a swirling protoplanetary disk around the newborn sun. Within this disk, a cosmic construction project began. Tiny grains of dust, no bigger than smoke particles, started sticking together. It was a slow, patient process of accretion. Clumps grew into pebbles, pebbles grew into rocks, and rocks grew into mountain-sized bodies we call planetesimals. For millions of years, these planetesimals smashed into each other, merged, and grew larger. It was a violent, chaotic ballet of creation. Through this gravitational demolition derby, the bigger bodies swept up the smaller ones, eventually clearing out their paths and forming the 8 planets we recognize today. From the rocky inner worlds like Earth and Mars to the gas giants like Jupiter and Saturn. Each one was sculpted from the remnants of that ancient cloud. So, once the planets were formed, how did they settle into such neat, predictable paths? It looks like a perfectly designed clock, right? Well, the credit for that goes to some fundamental laws of physics, most famously described by Isaac Newton and Johannes Kepler. Think of it like a cosmic tug-of-war. On one side, you have the immense gravitational pull of the sun, constantly trying to pull everything into it. On the other side, you have the planet's own forward momentum, its inertia, trying to fly off into space in a straight line. The perfect balance between these two forces is what creates an orbit. It's not a perfect circle, but a slightly stretched out oval known as an ellipse. Centuries ago, Johannes Kepler figured out the rules of this celestial dance. His laws revealed a stunning harmony. First, he found that planets move faster when they re-closer to the sun and slower when they re-farther away. Second, he discovered a beautiful mathematical relationship. The farther a planet is from the sun, the longer it takes to complete one orbit. This predictable clockwork motion made the solar system seem like a perfect, eternal machine. For centuries, we believed this cosmic order was absolute and would last forever. But as we'd soon discover, there's more to the story than just the sun's gravity. Gravity isn't just a one-way street from the Sun to the planets. Every single object in the solar system is pulling on every other object. The planets are constantly tugging on each other. Jupiter, the king of the solar system, pulls on Saturn. The Earth pulls on Mars. Even tiny Mercury exerts a gravitational influence. Now, most of these nudges are incredibly small, almost insignificant on their own. But over millions and billions of years, these tiny nudges add up. And this is where things get really interesting, with a concept called orbital resonance. Imagine you're pushing a child on a swing. If you push at just the right moment in each swing, you add energy, and the child goes higher and higher. That's a resonance. In space, the same thing happens. When the orbital periods of two bodies form a simple ratio like one planet taking exactly twice as long to orbit the Sun as another, their gravitational nudges happen at the same points in their orbits over and over again. This can be a force for stability. Look at 3 of Jupiter's largest moons, Io, Europa and Ganymede. They are locked in a perfect 1-2-2-2-4 resonance. For every 4 orbits, Ganymede completes, Europa completes 2, and Io completes 1. This regular, repeating pattern keeps their orbits incredibly stable over eons. It's a beautiful example of gravitational harmony. But resonance can also be a wrecking ball. It can be a force of pure chaos. A fantastic example of this is found in the asteroid belt between Mars and Jupiter. If you look at the distribution of asteroids, you'll see strange empty lanes. These are called the Kirkwood gaps. These gaps correspond to places where an asteroid would have an orbital resonance with Jupiter. Any asteroid that strayed into one of these zones would get a rhythmic gravitational kick from Jupiter again and again until its orbit became so unstable that it was flung out of the asteroid belt entirely. Jupiter, the great protector, also acts as a cosmic bouncer, clearing out the unruly parts of the cosmic dance floor. So, what does this all mean for us? It means that from its very birth, our solar system has been walking a tightrope between perfect order and complete chaos. On the timescale of a human life, or even all of human history, the planets seem to follow their paths with unwavering precision. We can predict eclipses centuries in advance. The system appears perfectly stable, but on cosmic timescales, millions of years, the story is very different. Every tiny gravitational nudge, every slight orbital shift accumulates. What starts as a whisper of instability can, over immense stretches of time, grow into a roar of chaos. This is the crucial takeaway. The solar system is not a perfect, eternal machine. It's a complex and fragile system governed by the subtle and unpredictable mathematics of chaos. The harmony we see is real, but it might just be temporary. The clockwork is ticking, but we're starting to realize it might not be ticking forever. The stage is set, the pieces are in motion, and the deep future of our home is far from certain. Thank you so much for joining me on this journey back to the beginning. If you're fascinated by the hidden dynamics of our universe, make sure to hit that subscribe button and ring the bell so you don't miss our next episode, where we'll dive into the shocking predictions of just how chaotic our solar system might become. See you next time.
Have you ever looked up at the night sky and felt a sense of peace, of perfect order? The planets glide in their orbits, seemingly forever. But what if I told you that this calm is an illusion? That our solar system is not a perfectly tuned clock, but a ticking time bomb, governed by the unpredictable laws of chaos. Today, we're pulling back the curtain on the cosmic drama unfolding right above our heads. If the solar system were a kingdom, Jupiter would be its mighty and unpredictable king. It's a behemoth, containing more than twice the mass of all the other planets combined. This immense size gives it a gravitational influence that dominates everything around it. In many ways, Jupiter is our protector, a cosmic shield. Its gravity acts like a giant slingshot. It's deflecting countless comets and asteroids that might otherwise be on a collision course with Earth. Many scientists believe that without Jupiter, life on our planet might never have had the chance to flourish, constantly being bombarded by catastrophic impacts. It's like having a giant bodyguard standing watch over the inner solar system. But this king is not purely benevolent. Jupiter's power is a double-edged sword. The same gravity that protects us also sows the seeds of instability. Take the asteroid belt, for example. Jupiter's gravitational pull has carved massive empty lanes within it, known as the Kirkwood gaps. Any asteroid unfortunate enough to drift into these zones gets a repeated gravitational kick from Jupiter until it's ejected into a completely new and often dangerous orbit. And it doesn't stop there. Jupiter can reach out to the far-flung Oort cloud, the source of long-period comets, and fling these icy bodies directly toward the inner solar system, turning our protector into a potential destroyer. Over billions of years, its subtle but relentless tugs on the inner planets accumulate, slowly, invisibly, setting the stage for future chaos. Jupiter isn't the only player in this cosmic game. It has a partner in its gravitational dance, Saturn. While Jupiter is the heavyweight champion, Saturn, though less massive, is still an immense world that acts as a secondary driver of chaos. Together, they form a powerful gravitational duo, their combined influence creating a complex rhythm that echoes throughout the solar system. A famous example of their partnership is a near resonance known as the Great Inequality. This pattern in their orbits means their combined gravitational tug on the other planets isn't perfectly balanced. It amplifies tiny shifts in other planets' orbits over incredibly long timescales. Think of it like pushing a swing. A tiny, well-timed push can send it higher and higher. Similarly, Jupiter and Saturn's combined pushes, over billions of years, could destabilize the orbits of the inner planets. Saturn's role is more subtle, sometimes reinforcing Jupiter's influence, sometimes counteracting it, but always adding another layer of complexity to the system's delicate balance. If you want to see the long-term effects of this gravitational chaos, look no further than the asteroid belt between Mars and Jupiter. It's not just a collection of rocks. It's a fossilized reminder of instability, a graveyard of failed planets. The rocks aren't evenly distributed. Instead, you see distinct gaps and clusters, a celestial map drawn by Jupiter's immense gravity. The Kirkwood gaps are the most obvious evidence. These are zones where an asteroid's orbit would be in resonance with Jupiter's. An asteroid in one of these gaps would orbit the Sun, say exactly twice for every one of Jupiter's orbits. This perfect timing means Jupiter gives it a gravitational nudge in the same direction. It's over and over, until its orbit becomes unstable and it's flung out of the belt entirely. And where do these ejected asteroids go? Sometimes they end up on a collision course with us. It's believed that many of the asteroids that have struck Earth, including the one that likely ended the reign of the dinosaurs, were originally pushed out of their stable orbits by Jupiter. The asteroid belt isn't just a relic, it's an active laboratory, showing us in real time how gravitational chaos sculpts our solar system. The chaos doesn't end with Jupiter and Saturn. As we venture further out, we find the ice giants, Uranus and Neptune, acting as the outer sculptors of our solar system. Neptune, in particular, has a dramatic history. Early in the solar system's formation, it's thought that Neptune migrated outward, and this journey completely rearranged the icy region beyond it, known as the Kuiper Belt. It scattered countless objects into wild, eccentric orbits. Neptune's influence is still felt today, It holds dwarf planets like Pluto in a tight gravitational lock. Pluto is in what's called a 3-2-2 resonance with Neptune, meaning it orbits the Sun twice for every 3 orbits Neptune completes. This resonance, this perfect timing, is what keeps Pluto safe. Without it, Pluto would have been chaotically ejected from the solar system long ago. So even here, in the cold, dark fringes of our system, we see that these gravitational resonances are a double-edged sword, capable of providing either long-term stability or ultimate destruction. The concept that ties all of this together is chaos theory. Now, in physics, chaos doesn't mean complete randomness or disorder. It describes a system where tiny changes in the initial conditions can lead to wildly different outcomes down the line. This is famously known as the butterfly effect. In the context of our solar system, this means that a change as small as a fraction of a millimeter in Mercury, Earth's orbit today, could over billions of years grow into a catastrophic change, altering the fate of the entire system. Astronomers have run thousands of computer simulations, and the results are sobering. They show that the inner solar system is, mathematically speaking, chaotic. The seeds of this instability aren't caused by some outside force. They are written into the fundamental mathematics of gravity itself, planted the moment the planets first formed. So what does this cosmic chaos mean for our future? These simulations have revealed several potential tipping points, cosmic time bombs that could one day go off. Mercury's fate is a major one. Because it's so small and so close to the Sun, it's extremely vulnerable to gravitational nudges from the other planets, especially Jupiter. A slight shift in its orbit could one day be amplified until it crashes into Venus, or, in some terrifying scenarios, even Earth. Another possibility is planetary scattering. A resonance between Jupiter and Saturn could destabilize the orbits of Mars or Venus, sending them careening through the inner solar system. In the most extreme simulations, entire planets are flung out of the solar system altogether, destined to wander the galaxy as cold, dark rogue planets. Now, it's crucial to understand these are not firm predictions with a date attached. They are possibilities, probabilities that are baked into the chaotic nature of our solar system. The familiar clockwork solar system we learn about in school is just a snapshot in time. On the grand cosmic scale, our home is a place of constant slow-motion change, where stability is temporary and chaos is the ultimate rule. It's a humbling thought, isn't it? We live on a tiny, fragile world in a system that is fundamentally unstable. But it's also a beautiful reminder of how dynamic and complex the universe truly is. The same forces that could one day lead to destruction are also the ones that sculpted the planets that protect us from impacts, and that make our solar system the incredible place it is today. Have you ever looked up at the night sky and felt a sense of perfect clockwork order? For centuries, we believed the planets followed their paths with divine precision. But modern science has uncovered a more unsettling truth. The solar system is a ticking time bomb, a chaotic dance where even a tiny nudge could lead to catastrophe. Today we're diving deep into the staggering possibility that our cosmic neighborhood could one day tear itself apart. Let's start with the smallest and most vulnerable planet, Mercury. Because of its tiny mass and its tight-hugging orbit around the Sun, Mercury is like a billiard ball on a wobbly table. It's incredibly sensitive to the gravitational pulls of its larger neighbors, especially Jupiter and Venus. But there's another layer of instability, thanks to Einstein's theory of general relativity. This theory predicts that Mercury's orbit isn't fixed. It actually wobbles or precesses over time. Normally, this wobble is harmless, but over billions of years, it can sync up with the gravitational rhythms of Jupiter and Venus in strange and unpredictable ways. Think of it like pushing a child on a swing. If you push at just the right moment, they go higher and higher. It's in the same way these planetary pushes could, over eons, amplify Mercury's orbital wobble to a dangerous degree. How dangerous? Computer simulations have run the numbers, and the results are startling. They suggest there's a 1 to 2% chance that Mercury's orbit could become wildly unstable within the next 5 billion years. Only in these nightmare scenarios, one of 3 things happens. Mercury could spiral directly into the Sun, ending in a fiery blaze. It could collide with its neighbor Venus in a planetary smash-up. Or, in the most terrifying outcome, it could be flung into a new path that puts it on a collision course with Earth. Imagine that for a moment. An entire planet crashing into our own. It wouldn't be an extinction event. It would be a system-shattering one. While the odds are low, the fact that this is even a possibility reveals a fundamental truth about the cosmos. Its long-term future is not written in stone. So if Mercury is the wild card, what does that mean for Earth? Are we safe? Well, for the most part, yes. The vast majority of simulations show our planet remaining in a relatively stable orbit for billions of years. Even if Mercury careens into Venus, Earth usually manages to stay out of the chaos, continuing its journey around the Sun unscathed. But usually isn't the same as always. In a small but significant percentage of these simulations, the chaos cascades outward. The destabilized Mercury first knocks Venus off its course. The newly erratic orbit of Venus then starts tugging on Earth, pulling our planet out of its safe and familiar path. In these rare but terrifying timelines, Earth either collides with another planet like a rogue Mars, or a displaced Venus, or worse, gets ejected from the solar system entirely. This isn't something to lose sleep over tonight, but it's a profound mathematical revelation. The stability we take for granted, the very ground beneath our feet, is not an absolute guarantee. We live in a solar system where, given enough time, the rules can change dramatically. Perhaps the most mind-bending outcome of all this chaos is planetary ejection. It sounds like science fiction, but the physics is real. A perfectly timed sequence of gravitational nudges and close encounters could act like a cosmic slingshot, launching a planet right out of the solar system. Because of its relatively low mass, Mars is the prime candidate for this fate. Imagine a chain reaction. Mercury's orbit goes wild, which perturbs Venus, which perturbs Earth, which then gives Mars the final gravitational kick it needs to escape the Sun's pull forever. If this happened, Mars would become a rogue planet, doomed to wander the dark, cold expanse of interstellar space, completely alone. While the odds are infinitesimally small, in theory, even our own Earth could one day face the same lonely exile. When chaos truly takes hold, collisions become almost inevitable. The most likely smash-up, according to the models, is between Mercury and Venus. Their orbits are the most susceptible to overlapping resonances. But other, more devastating possibilities exist. A collision between Mercury and Earth is rare, but as we've discussed, catastrophically possible. A collision between Mars and Earth is another scenario that pops up in these unstable futures. It's crucial to understand that we are not talking about asteroid impacts. An asteroid might cause a mass extinction, but a planetary collision is an event on an entirely different scale. It would be a creative force of destruction, fundamentally reshaping the solar system. Atmospheres would be stripped away, new moons could be formed from the debris, and the orbits of the remaining planets would be forever altered. A single collision could send a shockwave of change across millions of miles. So why can't we just predict what will happen and be done with it? The answer lies in the beautiful and frustrating field of chaos theory. There's a concept in physics called the Lyapunov time. It represents the time scale over which a system is predictable. For our solar system, that time is surprisingly short, only about 5 million years. This means we can predict the positions of the planets 100 years from now with incredible accuracy. We can even do it for 10,000 years. But once you try to look beyond 5 million years, tiny uncertainties in our measurements get magnified exponentially. It's the classic butterfly effect on a cosmic scale. It's a difference in Mercury's position today that is smaller than an atom could, over 1 billion years, be the difference between a stable solar system and one where Earth is on a collision course. Beyond that 5 million year horizon, the future isn't a single deterministic path. It's a fog of probabilities. As if all this planetary instability wasn't enough, the Sun itself throws a wrench in the works. Our star is constantly losing mass through the solar wind, sending a stream of particles out into space. It's not much, but over billions of years, it adds up. As the Sun gets lighter, its gravitational grip on the planets weakens. This causes all the planetary orbits, including Earth's, to slowly drift outward. This gradual expansion might seem harmless, but it changes the delicate gravitational balance of the whole system. The orbital resonances, those rhythmic pushes between planets, shift and change. In essence, the Sun's own evolution is slowly but surely pushing the solar system closer to the edge of instability, making chaotic outcomes more likely as time goes on. This brings us to the ultimate unanswerable question. We know the solar system's story won't last forever, but we don't know how it will end. Will it be a dramatic finale of planetary collisions, a quiet exodus of ejected planets wandering into the void, or just a long, slow decay as everything drifts apart? Right now, we simply cannot say for certain. The mathematics of chaos places a fundamental limit on our knowledge, creating a veil beyond which we cannot see. All we can do is continue to map the probabilities, explore the what-ifs, and stand in awe of the immense, unpredictable, and chaotic universe we call home. The one thing that's certain is that the cosmos is far more dynamic and surprising than we ever imagined. We often look up at the night sky and see a clockwork universe, planets tracing the same familiar paths year after year. But what if I told you this stability is an illusion? The solar system is a ticking time bomb of chaos, and Earth's future is far from guaranteed. Today, we're peeling back the curtain of cosmic time to ask a terrifying question. How will our world end? Let's start with some good news, a bit of immediate reassurance. For the next few million, even hundreds of millions of years, Earth's orbit is rock solid. You won't wake up tomorrow to find us on a collision course with Jupiter. The cosmic dance is slow, and the changes we read talking about unfold over timescales that are almost impossible for our minds to grasp. But, and this is a big but, the solar system's stability is not absolute. Over eons, tiny, almost imperceptible gravitational nudges accumulate. Think of it like a tiny, persistent wobble in a spinning top. For a long time, it seems fine. But eventually that wobble can grow, sending the top spiraling out of control. The same forces that make our solar system a chaotic system could one day ripple outward from the inner planets and reach us. And believe it or not, Earth's long-term fate might be tied to the smallest planet of them all, Mercury. It's the fly in the ointment, the wild card in the deck. Because of its tiny mass and its proximity to the Sun's immense gravity, Mercury's orbit is the most unstable. Over the next 5 billion years, scientists have calculated a slim, but very real, 1 to 2% chance that Mercury's orbit could become so elongated that it crosses the path of Venus. What happens then? Well, if Mercury collides with Venus, it would be a spectacular cosmic fireworks show, but Earth would likely be fine, a distant spectator to the crash. However, there's another, more terrifying possibility. If Mercury misses Venus, its chaotic journey could continue, and its new path could intersect with our own. A collision between Mercury and Earth would be utterly final. The impact would be so energetic it would vaporize the crusts of both planets, melting them into a single, glowing ball of magma and scattering debris across the inner solar system. Life as we know it would be extinguished in an instant. It's an extraordinarily rare event, a true cosmic longshot. But the fact that it's possible at all is a sobering reminder that nothing in the universe is truly safe. Even planets are not immune to the roll of the cosmic dice. But even if we dodge every chaotic bullet the solar system can fire at us, there's another threat. One that is not a matter of if, but when. Our own sun. It's the source of all life on Earth. But it will also be the agent of our planet's destruction. You see, the sun is a star, and stars have a life cycle. Right now it's a stable, middle-aged star, but it's slowly, steadily getting hotter. Over the next billion years, the sun's brightness will increase by about 10%. That might not sound like much, but it's enough to trigger a runaway greenhouse effect on Earth. Our oceans will begin to boil, as the water vapor filling the atmosphere and trapping even more heat until every last drop of liquid water is gone. Earth will become a sterile, superheated desert, like a more extreme version of Venus. Life will be long gone, and it gets worse, around 5 billion years from now. The sun will exhaust the hydrogen fuel in its core and begin to swell, transforming into a colossal red giant. It will expand so much that it will engulf Mercury and Venus completely. What about Earth? Our fate hangs in the balance. Some models suggest the sun's expansion and loss of mass will push Earth into a wider, safer orbit. But others predict we won't be so lucky, and our planet will be swallowed whole, vaporized within the fiery atmosphere of our dying star. Even if Earth physically survives, it will be a scorched, molten cinder, orbiting inside a giant star. The cradle of life will become its tomb. Long before the sun swallows us, the increasing solar radiation will have stripped away our atmosphere, leaving our world naked and exposed to the harshness of space. Stellar evolution is not a possibility, it is a certainty. So we have two executioners waiting for us: the slow, predictable aging of our sun, and the sudden, unpredictable violence of planetary chaos. Which one gets us first? In simulations where chaos truly runs wild, Earth's odds of survival plummet. We've talked about a collision with Mercury, but that's not the only danger. Imagine a scenario where a destabilized Venus, thrown off course by Mercury, ends up on a collision course with Earth. It's rare, but it's in the models. Or what if Mars, our little red neighbor, gets nudged into a new resonance with Jupiter and drifts into our path? But direct collisions aren't the only way for chaos to doom us. Sometimes a near miss is just as bad. A close gravitational encounter with a rogue Venus or Mars could act like a cosmic slingshot, drastically altering Earth's orbit, could pull us closer to the sun to be roasted. Or, and this is a truly mind-bending idea, it could fling us out of the solar system entirely. Ejected. Cast out into the lonely, frozen darkness of interstellar space. Can you imagine our world? Adrift between the stars? A rogue planet? It would be a catastrophe for all surface life. But deep beneath a shell of ice, miles thick, powered by the residual heat from our planet's core, some form of life might, just might, cling on in subsurface oceans. A ghost of a world, carrying a secret arc of life through the galactic void. This paints a stark and unavoidable picture for the future of life, and for us. The end of Earth's habitability is a guaranteed event. The only question is how it happens. If the sun wins the race, our biosphere will be sterilized by rising temperatures within the next billion years or so, long before the most extreme orbital chaos has a chance to unfold. But if chaos wins, a planetary collision or ejection could happen much, much sooner, though the odds of that in any given millennium are thankfully tiny. For humanity, or whatever we evolve into, the message is clear. Staying on Earth forever is simply not an option. At some point, our species must confront the monumental task of leaving our cradle and expanding beyond our home planet. It's easy to dismiss these events as impossibly distant, as abstract sci-fi scenarios that have no bearing on our lives. But let's put it in perspective. Modern humans have been around for about 300,000 years. The whole of recorded history is just a few thousand years. Against the billion-year timescale of planetary dynamics, our entire existence is less than the blink of an eye. We are a fleeting moment on a temporary world. But we have one advantage: knowledge. We are the first species on Earth that understands these cosmic timelines. We know about orbital chaos. We know about the sun's evolution. If our civilization can survive its own challenges long enough, this knowledge could be our ultimate salvation. It will guide our strategies for survival, whether that means colonizing Mars, building self-sustaining habitats in space, or one day undertaking the incredible journey to another star. The fate of the solar system isn't just an academic curiosity. It's a profound reminder of our place in cosmic time and a motivator for our future. So while our world will remain a safe and stable home for countless generations to come, we must accept a fundamental truth. We are living on borrowed time. The universe is a dynamic and sometimes violent place. The slow march of stellar evolution will one day erase our world. The roll of the chaotic dice could one day erase it much sooner. Both possibilities lead to the same conclusion. Earth is not eternal. Its time as a garden of life is finite. For now, we can cherish this beautiful, fragile home. But we should also look to the stars, not just with wonder, but with a plan. Because permanence is an illusion, and survival will ultimately mean moving on.
For thousands of years, we looked up at the night sky and saw perfection. The planets, those wandering stars, moved with the precision of a divine clock. The idea that this beautiful, orderly dance could ever fall apart, that planets could crash into each other, would have been unthinkable. But science is a journey of discovery, and the story of how we uncovered the hidden chaos in our own solar system is one of its greatest tales. It's a story that takes us from the mind of Isaac Newton to the immense power of modern supercomputers. In 1687, Isaac Newton gave us the rulebook for the cosmos, the law of universal gravitation. Suddenly, the elegant waltz of the planets could be described with mathematics. Newton's equations suggested that if you knew the position and speed of every planet, you could predict their movements forever. This created a powerful vision of a clockwork universe, a perfect machine set in motion and left to run for eternity. For many, this was proof of a flawless design, a solar system guaranteed to be stable and everlasting. But there was a hidden catch in Newton's beautiful equations. Solving the motion of two bodies, like the Earth and the Sun, is relatively simple. But add just one more planet, say Jupiter, and everything gets wildly complicated. Every planet pulls on every other planet, all at the same time. This tangled web of gravitational tugs is known as the unbody problem, and it has frustrated mathematicians for centuries. In the late 1700s, the brilliant French mathematician Pierre-Simon Laplace tackled it. He concluded that the solar system was fundamentally stable. He believed that any small wobbles in a planet's orbit would eventually be corrected by the gravitational pulls of the other planets. It was a comforting idea, and for over 100 years the scientific world agreed with him. The clockwork universe seemed safe. Then, at the end of the 19th century, another French genius, Henri Poincaré, found a crack in this perfect celestial machine. While wrestling with the unbody problem, he made a startling discovery. He found that the orbits of planets could be exquisitely sensitive. A tiny, almost immeasurable change in a planet's starting position or speed could lead to completely different, wildly divergent paths millions of years down the line. This was the birth of what we now call chaos theory. It meant that even with perfect laws of physics, long-term prediction might be impossible. Poincaré showed that the stability of our solar system wasn't a guarantee, it was a question mark. His work hinted that the cosmic clock might not be so perfect after all. It was a revolutionary idea, but it was so far ahead of its time that it would take another century and a new kind of tool to truly understand its implications. That tool was the computer. Before the digital age, calculating planetary orbits over billions of years was simply impossible. A lifetime of hand calculations wouldn't even scratch the surface. But by the 1980s and 90s, computers had become powerful enough to take on the unbodied problem in a way Poincaré could only have dreamed of. Astronomers could finally build digital models of the solar system and let them run, simulating the gravitational dance of the planets for eons. They could fast-forward time, watching billions of years tick by in just a few days of computation. The results that came back were stunning and, for some, deeply unsettling. The simulations proved Poincare was right. On very long timescales, the solar system is chaotic. The orbits of the inner planets, especially Mercury, were not perfectly stable. They could wobble, drift, and change in unpredictable ways. The comforting certainty of a clockwork universe was officially replaced by a much more complex and uncertain reality. The ultimate confirmation came in 2009. An astronomer named Jacques Lascar and his team ran thousands of simulations, each one a slightly different version of our solar system's future, stretching out over 5 billion years. Think of it like running the same experiment over and over to see all the possible outcomes. In the vast majority of these digital universes, everything was fine. The planets continued their stately procession around the Sun. But in about 1% of the simulations, something dramatic happened to Mercury's orbit. Already the most eccentric of all the planets became dangerously unstable. Its path would stretch out so far that it crossed the orbit of Venus. In some of these chaotic scenarios, Mercury would crash into Venus. In others, it would be flung into the Sun. And in a few terrifying cases, Mercury's rampage would destabilize the entire inner solar system, sending Mars on a collision course with Earth. This was a profound moment in the history of science, astronomy. The science of prediction was now telling us that the future is governed by probability. We can't say for certain what will happen in 5 billion years. We can only talk about the chances, the odds. There is a 99% chance that the solar system will remain much as it is today, but there is a 1% chance of catastrophic collisions. The clockwork is gone, replaced by a cosmic game of chance. Don't worry, the odds are overwhelmingly in our favor, and we're talking about timescales longer than the Earth has existed so far. Still, the knowledge that our cosmic home isn't perfectly safe forever changes our perspective. This journey, from Newton's perfect order to Lascar's probabilistic chaos, has completely transformed our understanding of the heavens. We've learned that the universe isn't a simple, predictable machine. It's a dynamic, interconnected, and sensitive system, where the tiniest influences can grow over time to have colossal consequences. The pull of a small asteroid, a slight change in the Sun's mass as it ages all. These factors feed into the complex dance of the planets. It's a bit like weather forecasting. We can predict tomorrow's weather with high accuracy, but forecasting the weather a year from now is impossible. The solar system, it turns out, is the same. We know where the planets will be next year, or in 1,000 years, but their fate, billions of years from now, remains uncertain. For scientists, this discovery was both humbling and incredibly exciting. Humbling because it revealed the fundamental limits of our ability to predict the future, even with the most powerful laws and tools at our disposal. But it was also inspiring because it unveiled a universe far richer and more complex than we ever imagined. The story isn't over. Today, astronomers continue to run even more detailed simulations. Adding in the effects of Einstein's general relativity, the influence of thousands of asteroids, and other subtle forces. Each new simulation paints a clearer picture of the deep, long-term fate of our solar system. We went from seeing the planets as perfect points of light in a clockwork sky to understanding them as part of a grand, chaotic, and beautifully complex system. And that, in itself, is a truly wonderful discovery.
Have you ever looked up at the night sky and wondered if it will all be there forever? The familiar planets, the steady glow of the sun. It feels permanent, doesn't it? But the story of our solar system is a story of time. Time so vast it stretches into the billions of years, a scale where even worlds cannot escape change. The planets we know and love will not orbit our sun forever. They are a temporary arrangement in a universe where permanence is just an illusion. So what is the endgame for our cosmic neighborhood? Where does the solar system go from here? Our journey into the far future begins with the one constant in all our lives, the sun. It's the heart of our system. But it's also our cosmic clock, ticking down to an inevitable transformation. For now, it's a stable, middle-aged star, but it's slowly, almost imperceptibly, getting brighter. In about 1 billion years, this increasing brightness will have a catastrophic effect on Earth. The oceans will boil away, the atmosphere will be stripped, and our vibrant blue world will be sterilized. The long story of life on Earth will come to an end. It's a sobering thought, isn't it? That the very star that gives us life will also be the one to take it away. But the sun's evolution doesn't stop there. Fast forward to about 5 billion years from now. The hydrogen fuel in its core will run out, and the sun will begin to swell, transforming into a red giant. Its outer layers will expand dramatically, engulfing the innermost planets. Mercury, the closest, will be the first to go, vaporized by the star's fiery embrace. Venus will follow. Earth's fate hangs in the balance. Some models suggest it might be swallowed whole, while others predict it could be pushed into a slightly wider orbit. But even so, it would be a scorched, molten rock, unrecognizable. What a spectacle it would be, a sky dominated by a colossal red star. After this dramatic, giant phase, the sun will finally die. It will shed its outer layers into space, creating a beautiful, glowing structure called a planetary nebula. What's left behind will be the sun's core, a white dwarf. Imagine an object about the size of Earth, but packing half the sun's original mass. It's an incredibly dense stellar ember, a ghost of the star that once was. This transformation will fundamentally rewrite the rules of our solar system. As the sun loses so much of its mass, its gravitational pull will weaken significantly. The surviving outer planets Jupiter, Saturn, Uranus, and Neptune will feel this change, slowly drifting outward into wider, more distant orbits. The once tightly knit family of planets will begin to loosen. The solar system will become a much larger, emptier place. And this is where things get truly chaotic. The sun's weaker gravitational grip, the delicate dance of the planets will become unstable. The subtle gravitational nudges that planets exert on each other will become much more significant over the immense timescales that follow. We're talking trillions of years. In this new, looser solar system, close encounters between the giant planets become more likely. Imagine Jupiter and Saturn passing near each other. Their immense gravity could act like a cosmic slingshot, flinging one of them, or even a smaller planet like Mars, out of the solar system entirely. It would become a rogue planet, doomed to wander the cold, dark emptiness of interstellar space, untethered from any star. Other planets might not be so lucky as to be ejected. They could be sent on new elliptical paths that cross the orbits of others, raising the possibility of planetary collisions. Though as orbits widen, these collisions become less likely. What about the smaller residents of our system? The asteroid belt between Mars and Jupiter and the icy Kuiper belt beyond Neptune will slowly be cleared out. Their members will either be thrown into the dying sun, collide with the remaining planets, or be ejected into the galaxy, just like their larger cousins. Over an almost unimaginable stretch of time, our once bustling solar system, with its 9 planets, countless moons, and belts of debris, may dwindle to just a few lonely survivors orbiting a dim white dwarf in the darkness. But the solar system doesn't exist in a bubble. We are part of a much larger structure, the Milky Way galaxy. Our sun, along with its planetary family, orbits the galactic center once every 230 million years. During this long journey, we pass through different cosmic environments. Sometimes we travel through sparse, empty regions, but other times we pass through denser star fields or near massive interstellar clouds. Over the next tens of billions of years, the chances of a close encounter with another star increase. A passing star wouldn't need to collide with our sun to cause havoc. Its gravity alone would be enough to disrupt the fragile orbits of the remaining planets, pulling them from their paths and flinging them into the galactic void. Some simulations suggest that over these vast timescales, the entire solar system could eventually be dismantled, piece by piece, by these galactic encounters. Our planetary family, born together from the same cloud of dust and gas, will ultimately scatter across the galaxy, each world going its separate way. Even the sun's final remnant, the white dwarf, isn't eternal. It shines not from fusion, but from leftover heat, like a glowing coal taken from a fire. Over quadrillions of years, a number so large it's hard to even comprehend it, will radiate away all its remaining energy, slowly cooling and fading. Eventually, it will become a black dwarf, a cold, dark, crystallized object, invisible against the black backdrop of space. By that time, any planets that manage to survive the chaos will be orbiting a dead star in absolute silence and darkness. The solar system, as we know it, or could ever recognize it, will be gone. All that will remain are scattered fragments, rogue worlds wandering the galaxy, cold stellar corpse, and the memory of starlight that was extinguished long, long ago. So what does this cosmic destiny mean for us, here and now? For humanity, living in what is essentially the solar system's youth, this knowledge is both sobering and incredibly empowering. It's a stark reminder that our home, planet Earth, is not eternal. Its stability is a temporary gift, and its habitability has an expiration date. This truth underscores the profound importance of looking beyond our world. If life, and specifically human consciousness, is to survive the universe's slow march towards decay, it cannot remain bound to a single, fragile planet. We must become a species that travels the stars, not just out of curiosity, but out of necessity. This long view of the future also teaches us a deep and powerful lesson in humility. The predictable orbits we plot, the apparent stability of the heavens that our ancestors worshipped, it's all a temporary balance in a system ultimately governed by chaos. We are living in a rare, stable moment. We take for granted the ground beneath our feet and the sun in our sky, but the universe is constantly in motion, constantly changing. We are not the masters of a static creation, we're participants in a dynamic, evolving cosmos. Realizing this helps us appreciate the preciousness of our current moment, this fleeting instant of warmth and life in the vast, cold emptiness of time and space. This brings us to the final and perhaps most profound question. The ultimate fate of the solar system isn't just about the physics of planets and stars, it's about perspective. We are, as far as we know, the first generation of life on this planet to understand these cosmic truths. To know that our sun will one day die, to know that even the orbits of the planets are not fixed, but are subject to chaos, to know that our entire system will one day dissolve. This knowledge forces us to ask, if everything we see around us is temporary, what is our role in it all? Are we simply fleeting observers, a brief flicker of awareness in a fragile system destined for oblivion? Or are we something more? Are we perhaps the seeds of consciousness that might one day transcend the fate of our homeworld and carry the legacy of Earth out into the galaxy? The solar system is not a machine built to last forever. It is a beautiful, intricate dance on shifting ground, where the quiet whisper of chaos can be heard in the background of every single orbit. From its fiery, violent birth to its eventual quiet scattering across the galaxy. The system we call home is just one chapter in a much larger cosmic story, a story of creation, relentless change, and inevitable decay. We are privileged to live at this specific moment in time, when the sun is warm, the earth is stable, and life is able to thrive. Billions of years from now, none of this will be left. But today, right now, we are here. We have the capacity to look up at the sky, to wonder about our place in it all, and, crucially, to understand it. And perhaps that's a simple act of knowing, of comprehending our own magnificent temporary homes, the most remarkable part of the entire story. Thank you for joining me on this journey to the end of time. If you found this perspective as fascinating as I do, consider subscribing and hitting that notification bell. There's a whole universe out there to explore together. See you in the next video.